Hello, everybody. This is going to be our second real full lecture. This one's still going to be a little bit shorter, which hopefully you will enjoy. Um, and we'll get through some important info, and I think this will be really helpful as we are able to finally get into some actual in-person welding this Friday. So, to start with, this is what we're going to talk about today. GMAW procedures, remember that's gas metal arc welding, um, and procedures and techniques, and then some of the common problems and how to correct them so that you will be able to have all that info when you get started on Friday. To start with, though, we do need to talk about some terms and kind of clarify these. We sort of briefly skimmed over a little bit about this in the first lecture when we was talking about power sources themselves. But now we need to talk about a little bit more of the specifics about the sort of parts of electricity that you are dealing with and what they all mean. And that'll help you understand what it is exactly that you're actually doing when you're doing this welding. So first off, amps versus volts. So an amp is a unit measuring the quantity of current, and then a volt measures the actual electrical pressure, if you want to think about it as pressure. The pipe analogy, I know I brought this up, but it's used a lot when you're thinking about or trying to explain electricity. So if you think about the water in a pipe, an amp is the amount of water flowing, like the gallons that are going to come out of it. And then a volt is the actual pressure of the water, as in if you have the tap fully open or just partially open. Or if you, like with a hose, you put your thumb over the end of the hose and that sprays out harder. That would be like increasing the voltage, if that makes sense. So I talked a little bit about this. The part of this that I was referencing was like the size of the pipe is what we were talking about. So if you are plugging into 110 volt electrical outlet, then you have a smaller pipe versus if you're plugging into a 220 volt. So hopefully that if you when you're thinking about electricity as we go along, that kind of water analogy and pipe analogy can prove useful. I know it is to me because it's still electricity is a concept that I'm continuing to try to understand. Another aspect of electricity that you will encounter with welding, if you've done any TIG welding, you've probably talked about this already, is AC versus DC power. AC stands for alternating current, DC is direct current. So the difference in these is actually a little bit easier to understand. Alternating current, as the name would suggest, it alternates. So the direction of the flow, the sort of positive to negative or negative to positive, that is changing very fast in milliseconds. So that hopefully this picture kind of helps to give you an idea. It's going positive to negative, and then it's going negative to positive, and back and forth and back and forth. DC is a current that only flows one direction always. So it's kind of more like a circle than a wave. So AC versus DC. Then we have constant current versus constant voltage. And this is the power sources themselves. The power sources themselves, generally speaking, can only do AC or DC. Now we have new ones that can do both, but set that aside. So they can only do AC or DC, and they are going to be only constant current or constant voltage. Again, now we have power sources that can do both, but let's think of it as two separate options, first of all. So a constant current power source, as the name suggests, it's pretty easy to remember, maintains the current. Now the current is how we talk about amperage. Again, the volume, the gallons of water that's available to you in a pipe. The constant current power source will maintain that amperage at a constant level, regardless of changes in voltage that might happen because of how you are welding. The constant voltage power source, again, as the name would suggest, maintains the voltage itself at a constant level, regardless of changes in the amperage. Constant current versus constant voltage, two other sort of categories to remember. This is all just the definitions, and then we'll get into why they matter, what they mean here. A little bit more about what constant current versus constant voltage actually means in practice. So first of all, this is as soon as you learn something, you got to unlearn it. That it's not actually constant per se. It is relatively constant. It's mostly constant. It is pretty much constant or kind of constant. It's easier to just think of it as one is constant or the other is constant, but you need to know that in reality, it's not 100% constant. It still is. There's fluctuation. So whatever it is, constant current or constant voltage, the power source itself, your welder itself, your box, that is monitoring the arc and making changes in order to maintain a stable arc condition. So it's either changing the amperage or the voltage in order to maintain a stable arc condition so that you can do the welding that you need to do. And again, this is another sort of learning and then unlearning. Newer machines, they will be able to pulse the current, or they use something called waveform control technology, and it's not that new anymore. I mean, some of our TIG welders can do have a waveform control. Those power sources are not truly constant current or constant voltage either. These are the sort of newer, higher technology where they can monitor and change both the voltage and the current at extremely fast rates in order to produce these super stable arc welding conditions. So it's all about maintaining a stable arc, the actual jump of electricity from your electrode to your workpiece. It's all about keeping that as stable as possible, no matter what you are doing, where your hand is with the welder itself, where the electrode is, how fast it is, what size metal you're welding. It's all about keeping that arc as stable as possible. So it's going to produce a quality weld. So that was our definitions. Hopefully now we'll get into some specific procedures and techniques. If you're following along in your book, this will be chapter 7 if you want to dive more into it. Again, we go with a couple of definitions. Extension versus stick out. These are two terms that you're going to hear used a lot with MIG welding. And they're kind of the same thing, but in practicality, in actual practice, they're different. And so you need to know what the difference actually is for when the situation might occur that you might need to be very specific about this. So technically, extension is the distance from the contact tip to the end of the electrode here. Now, some welders are going to be a little different with this gas nozzle and contact tip setup. Some of them, the gas nozzle will look like this, where it'll be below the contact tip itself. Some of them, they're more flush, and some of them are even with the contact tip is sticking out a little bit, and the gas nozzle stops right about here. So that's why this difference between electrode, stick out, and extension sometimes doesn't matter, but sometimes it does. If you have any questions about this, it will probably be helpful to look at some of the welders in person when we get into the shop, and then you might understand a little bit more what this means and when it comes into play. But technically, we want you to know that extension is from the end of the contact tip to the end of the electrode, while stick out is going to be, it's visible stick out is what it's usually called, what you can see. So if your gas nozzle sticks out beyond your contact tip already, then you're going to see a slightly shorter amount of electrode there, and that's going to be your stick out versus your total extension. Again, if we have questions about that, maybe jot down a note of something you don't understand and make a note to check it when you get in to actually look at a real machine. So what extension does here, increasing extension, so remember the amount from the contact tip to the end of the electrode, increasing that, making it longer, means there's more what's called resistance heating. So there's more heating that happens in the wire itself, in the electrode, and that translates to a lower amperage arc overall. This can be useful if you're welding thinner material and you want to prevent burn through. Decreasing the extension, coming in super short, super close to your base metal here. That means there's less wire that's going to be resistance heating. It's going to be kind of, I don't know, using up the electricity before it hits the metal, if you want to think of it that way. This means there is an increased amperage in your arc, and that means more penetration, so good for thicker material. So what this really means in practice is that if you have thinner material, it's usually helpful to be a little farther away. If you have thicker material, you want to be super close. That's where it comes into in real practice. I mentioned a little bit about welding direction in the first lecture last week, backhand welding or pull welding, and then there's push welding. So backhand welding is your weld is going to be making your weld in this direction. This is the travel direction. And the gun is pointing back to the weld while traveling in the opposite direction. So like I said, when you're first learning here, you can try it in both ways, and there's going to be a way that's more convenient for you or more comfortable for you. But there are times when you want to use one or the other, and knowing what they translate to, again, as far as what's happening in the weld or what the weld's going to look like, can be helpful if you're having trouble with one thing. Maybe switch the direction that you're welding and see if that helps. So, for example, backhand welding, you have a more stable arc and less spatter and deeper penetration. So obviously more stable arc and less spatter are always going to be good things. But again, if you're on thinner material, you might not want that deeper penetration. So you might want to switch instead to push welding in order to make sure that you don't burn through your material. That's why you want to know what these different positions actually do. And forehand welding or push welding, that's the opposite. So here's your weld right here. You're going to be laying your bead this way. You're traveling to the right. And your welding gun points forward in the direction that you are traveling. Now, this is specifically recommended for if you're welding aluminum, which maybe we'll get to in the future. And also if you are welding with different welding deposition modes, namely spray transfer or pulsed spray transfer modes. Now, we haven't covered welding deposition modes yet, so kind of can set that aside mentally, and we'll get back to it there, but wanted to introduce it real quick. So the results of your weld compared to backhand welding, you are going to get more spatter, and you get less penetration, so it can be good for thinner. The other thing that's really nice about push welding is the better seam visibility. Again, this might make more sense to you once you have a welder in your hand, but you'll be able to see where you're going a little bit easier because you're not blocking with the direction that you're traveling, whereas with backhand welding, you can't actually see right here. You can only see where the weld is that you just laid down, whereas this one you can see where you're going. So that is a little bit of a difference. And it can sometimes make a weld easier to do if you're doing push welding. Another thing that's going to really affect your weld, namely the weld penetration, the bead form, and the bead appearance, it's not just aesthetic. The bead appearance translates to a good bead or a bad bead. That's what welding inspectors are looking at, the appearance to see if it's right or not. So that is important more than just it looks pretty. So the gun angle, there's two different gun angles that you're going to be working with. First, the transverse angle or the work angle, and that is when this one the weld bead is going this way, towards you. This one the weld bead is side to side like this. So this is where the weld is right here. Your gun is right here, and it's the angle this way or this way. Okay, that's the transverse or work angle. Generally, it ranges from 0 to 45. But transverse angle, the weld bead's right here, your seam's right here. You're welding in between these two pieces together, and it's this angle side to side that you're setting up. Now, the longitudinal angle here, That's the travel angle. That is where the weld is happening this way. And you have your gun here. So this is the work. This would be the work angle here. Then your travel angle is this way. So work angle, travel angle. Hopefully that makes sense. But you'll, again, you're gonna, when you're doing this in reality, you're gonna know what those mean a little bit more. But just know that there might be references. You're gonna see references to transverse angle or longitudinal angle, and you need to know which angle that means. And adjusting those angles can be a necessity if you're following a specific welding procedure, or they can make the weld better or worse if you adjust them. All right, a little about bead patterns, which we mentioned in the last lecture as well. So a stringer bead is what you've heard that when you're doing your stick welding. It's just sort of a basic flat kind of bead. With MIG welding or flux core, it's not just a drag generally. You still have to have some side-to-side motion, but it's just much, much smaller side-to-side motion. So a stringer bead is almost dragged, but not quite. So you either do this kind of zigzag idea, or you do kind of a small circular motion. And as I mentioned when we were talking about welding patterns before, it's more of a, like, how you think about it in your mind and the best way that translates for you into what you're actually doing. So you can think about it either in this zigzag motion or this kind of circular motion, and you'll try it out and see which one makes most sense to you. Now, a weave bead, this is going to be the much larger bead. You might hear it called a wash bead or an oscillation bead. So this is where you actually are weaving it side to side. It's going to be wider than a stringer bead. And this picture is really helpful because it has these like round circles kind of on either end. And that indicates this sort of stop or dwell at the end of each weave. It's a very slight, it's not like super slow, but you do stop a little bit at the end of each weave motion. And that's going to fill in the metal without having undercut. We're going to talk specifically about what undercut is and why it's important to avoid it a little bit later on. But that dwell, that stop at the end of a weave, is an important part of avoiding certain problems in your weld for now. Now, a couple of these next couple of slides are they're more an example of something in your book that might be useful for you later on. These pictures are all going to be in the book. We don't do any big multi-pass welds in this class, so this isn't really something that we have to be super concerned about, but it is something you will want to know for later on, especially if you get, if you're going to pass any of the certifications, get any of your certifications and stuff. So you're going to see references to these different angles and these different specific patterns that you want to follow. So this is showing you like the passes in order that you do. So you do this first pass, the root pass down here at the bottom. Then you do a slightly larger, a bigger weave right over the top of it. You do the third one on one side, the fourth one on the other side there. So, and you have these different, these are where this longitudinal angles come into play. So it shows you the different angles that you need to have for these different welds. So we're going to go through a couple of these really quick that are just like to know for the future. This is for multi-pass horizontal bevel and V-groove welds. It gives you all the angles, everything you need to know. Here's a fillet weld, different angles for that. And then we're going to get into a little bit more of what will be helpful for you guys to know. Again, I mentioned in 212 is what we really focus on doing the vertical welds. In 211, we're going to focus on flat and horizontal. But still, this is useful information for everyone. This is how when you're doing a vertical up weld, you start from the bottom and you go up. The difficulty is that you're kind of trying to keep this molten liquidy pool of weld. You have to push it up against gravity when it's going to want to fall down. So you're kind of supporting it from the underside and pushing it up. And again, if you're doing multi-pass, we're talking about that bead placement. Same as for flat and horizontal welds, the ones that these ones here. So the bead placement is going to be the same. Again, log that away for future use. For vertical down, as it would suggest, you're welding from the top down. So in this case, again, you're still struggling with gravity in that molten liquid pool of weld metal. But in this case, you're instead of pushing it up, you're sort of supporting it and letting it fall down from the underside in a more controlled way. Hopefully that helps to sort of conceptualize how this is going to work for when you try that out. So that was all from chapter 7. I believe we're going to skip all the way to chapter 17. I think that I have a specific, organization in mind that I think is helpful. So we skip around a little bit in the book, as I mentioned. So these are going to be, we're talking about defects and corrective actions mainly. We're kind of picking some sections from chapter 17. So if you go ahead and read chapter 17 on your own, you'll kind of read more than we really cover in this lecture. So one of the big main defects is going to be porosity. Probably all encountered that in some form or another in your stick or oxyacetylene welding. So this, for GMAW, for MIG welding, the porosity is often formed by gas entrapment during solidification. It can be caused by different gases. These are a lot of these are just in the air, in the atmosphere. It's not necessarily just the welding gas that you are using. The way that this can be addressed and eliminated is by having proper flow rates. So that would be adjusting your regulator. I mentioned that you don't want to go too high with the flow rate. That can cause problems as well as being too low. But that's like first thing you should check if you see a lot of porosity. Is check your flow rates. Also, cleaning the base metal before welding is going to be super helpful. If you're having a lot of problems, it could be, like oil left on the base metal, or it's super rusty or had paint on it, stuff like that. All those can cause porosity. Another very important thing to check is checking the gas nozzle and contact tip. This is where those MIG welding pliers are going to come in really handy. The gas nozzle is this kind of cone shape. The contact tip fits inside of it. The gas nozzle is going to collect a lot of spatter around the inside. And it just, as you're welding, it just sort of builds up in there. So you're going to want to occasionally clean that out. That really does affect your weld. And I said you should check your flow rate, but I'm changing that. The first thing you should always check if you're having a problem with your weld is your gas nozzle and the contact tip, because the end of the contact tip also sort of develops or accumulates spatter on the end, so you want to clean that off as well. It can cause a lot of problems. It disrupts the gas flow. Those pieces of spatter can fall out into your weld and cause problems with porosity. And you can also, fuse your electrode wire. It's not going to feed out cleanly. It's going to stick to the spatter that's built up on your contact tip. So all of that is something you just have to periodically kind of check and clean. We also do have some kind of gel-like substance that you can use to coat. You can sort of dip your nozzle in there, and that helps prevent some spatter. So we could try those out too. It helps prevent the buildup of spatter on your gas nozzle. So spatter itself on the weld, this comes from, you see all these kind of little bumpy bits around the weld. It comes from metal particles that are expelled during the weld that don't, for one reason or another, actually form part of the weld. So they should have been in the weld, but they're not. It's not a huge concern. It doesn't necessarily affect the strength and quality of the weld itself, but it can interfere with some weld testing and stuff. A big problem can be if you are painting or coating it afterwards, those little pieces of weld spatter aren't fused very well to the base metal, so they can chip off over time, and then you have an exposed part that wasn't painted or powder coated. Generally, you do want to clean spatter off, especially if it's super excessive, like you can see in the picture here. Another problem, this really only comes up with FCAW, with flux core arc welding, is the slag inclusions. You've all encountered that with your stick welding, because that uses a similar, the coating on the outside of your stick is the same as what's inside of a flux core electrode. So that's where the slag comes from. Flux core does create a slag over the top, whereas MIG welding does not. So slag is trapped in the weld metal, can be caused by improper cleaning, a bad joint design, slag flooding ahead of the arc. So that would be something wrong with your setup, with your process that you're doing, or entrapped pieces of the electrode coating just coming off from whatever. There is some slag inclusion that is acceptable. Different welding codes will limit the amount, so you don't want something like this that's big and pretty major. But sometimes it's a little bit of slag inclusion is acceptable and will still pass inspection. Another problem, incomplete fusion or lack of fusion. Another thing I'm sure you've encountered before. This means that proper fusion did not occur between the weld metal and base materials, or just between adjoining weld beads if you're doing a multi-pass weld. So this is between the weld base material and the weld bead itself. There's a lack of fusion there. This is some lack of fusion, looks like, in between the weld. Maybe that is between weld beads. Couple different causes for this. Too low of a current, or your amperage. Maybe a lack of access to all weld joint surfaces, or maybe you had like a super tight groove, or a little bit too small of a V and you couldn't get your welder in there very well. Inadequate pre-weld cleaning of the joint surfaces can be a problem too. You had oil or paint or something like that there that was getting in the way. Most of this incomplete fusion is internal, and so you're not going to see it necessarily through a visual inspection, but it is a serious defect. So if they're doing any kind of further inspection and that becomes visible, then that's weld is going to be immediately disqualified. And if you're doing your weld test for a certification, obviously you do a destructive testing. And if you see any incomplete fusion like this, that weld isn't going to pass. You're not going to get your cert. So it is an important, it's a very bad problem to have. Unfortunately, it's not always visible right away. Another problem is incomplete joint penetration. So this would be in the root pass of a groove weld, or just if it's a single pass weld, the first weld that you do, the only weld that you do, where the weld metal does not penetrate through the thickness of the joint. This again is caused by insufficient welding heat, or too low of a voltage when you're adjusting the voltage on the front of your machine. It can also be a bad, poor joint design. A bad bevel angle in your weld, and poor control of the welding arc, your actual process when you're doing the welding, if you're not doing that very well. This you can see in visual inspection is going to be a cause for rejection under almost any weld code, so something to be avoided. Cracks in your welds are very bad. These don't tend to come up when you're just welding mild steel, which is what we're going to be welding this whole time. They come up a lot more when you're welding, either stainless steels or other kinds of alloys. But still, obviously, good to know. And they come up when in aluminum as well, of course. Cracks are the most serious discontinuity. So these are the biggest no bad problem. If you have sharp cracks on the end of a weld, or the sharp ends rather on the crack, like these, not just a big hole right there, the crack is gonna continue lengthening and lengthening until the whole thing breaks. And any crack, regardless of size, is rejectable under all welding codes. These are just some kinds of different ones. It can be straight down the weld like this. It could be across the top of the weld. You can have a whole finished weld and it crack across the weld there. In a fillet weld like this, you can have a crack happening in between the base metal and the weld metal there. Lots of different ways they can occur. Always bad. I said we were going to talk about undercutting. So overlap and undercut. These are two examples. This is overlap. This is undercut. So overlap is where the weld metal protrudes beyond the weld toe or the weld root. We'll get into again a little bit later those more specific terms and what they mean. But for now, you can see that this is like globbed over the edge, and it's not. It's too much weld. Basically, is what overlap is. Too much weld metal. Undercut is the opposite. It's where there's too little weld metal. Both of them are caused by improper technique. So undercut's the one that I probably see the most often in students' welds. So this right here is undercut. How you can see there's kind of space here where there's not metal, and here along the edges. So what's happening there is that you didn't fill in enough metal, because when you're welding, part of your base metal is melting as well into the weld, and then you're adding that weld material from your electrode. But if you don't add that metal back in that you melted out of the base metal, then that's when you get this undercutting. So you have to make sure that you add back in enough of the weld itself. This is obviously pretty obvious, I think, a source of a lack of strength basically in the weld. So this could be where it could fail or break. Overlap is too much weld, but it still has the same problem. It actually causes weak points here, whether you're overfilling it here. There's a weak point here where there's it's just not as strong, basically. So remember when I talked about the weave bead pattern, how there's those pause points at either end of that weave. That's what you can do is going to help to avoid having this undercut. And I'm sure that everyone's going to experience it, on one time or another. It is going to be a weld that, I have to toss out. It doesn't pass, doesn't count towards completing that weld. And we'll discuss in the specific circumstance with whatever weld you're doing, how to fix that. But generally, it's not enough metal being added back into the weld. Underfill and excessive reinforcement, again, two opposites, two sides of the same thing. Underfills when the weld face, the actual top surface of the weld, is below the surface of the base metal. So you have your base metal here, the weld face is down in here. So it's underfilled below the face of the base metal, not good. The weld size is less than required, so that's bad. It's gonna not pass inspection. And then excessive reinforcement is similar to overlap, as where there's too much, it's more weld than is necessary to fill a groove weld. And again, you're actually creating weak points here in the weld on either side of that excessive reinforcement. It's only on thicker steels. It doesn't really come into play on thinner stuff. But too much weld is just as bad as too little. Concavity or convexity is kind of the same thing, but a little bit slightly different. So that's the actual weld bead itself, or the weld pool itself, being too concave, kind of just sucking back in the middle, or being too much there, so it's too convex. Again, that is acting as a stress concentration there, having too much convexity, and then the concavity, actually, I should edit this. The concavity is what weakens the weld, so it's not strong enough to hold the loads that it was designed for. So both of them are weak, cause weak points in the weld. It's either too little or too much. Got to get in that Goldilocks spot. So this is another chart in your book that I think is really, really helpful. This is something like that you could refer to while you're in the middle of your welding in the lab. You have some problem here. And then this can kind of give you some guidelines on what these different parameters do to affect the different aspects of your weld. So can be helpful to refer to. All right, that was the end of our lecture. As always, if you have any questions, feel free to email me or send me a message through Canvas. And we will be meeting on Zoom on Thursday at the same time at 6 o'clock, our regular time. If you have already watched this, then you can ask me any questions you may have then, and we'll discuss it then. Or we will also go through the entire lecture again. So you can sit around for that if you want to go over it twice. But that is it for now. Hope you have a good week. See you on Thursday. All right.